Hi, everyone. Uh, let's see, I think this is all set up. If you have any trouble hearing me, just let me know. I'll give people another minute or two to log on. Okay. All right, just some general reminders. Try to have homework 7 in if you haven't already. Lab 9 is up. It's based on material we're going to talk about in this lecture. So after this lecture is over, you could get started on that. The TAs are going to have their normal lab times this afternoon and evening if you want to ask questions during that time, or you can also just set up an appointment with me or with them. Um, Hopefully everyone is either able to join these live streams or view the recordings. If you're having trouble doing one of those, or you're having trouble just technical problems with the assignments, please let me know. We can try to figure things out. I think things have been going okay for most people, but I'm sure I'm missing some problems people are having, so please let me know. Okay, so I'm going to try something slightly different for this this live stream. I'm going to go through the lecture in sections of about maybe 10 minutes or a little longer. And then we'll stop, have like a brief quiz you can answer in the chat, and I'll also answer any questions. So feel free to answer questions at any point, but I'll mostly try to batch them up and do them at the end of these sections. We'll see how that experiment goes. Okay. So switch over here. All right. So today we're going to be talking about a new type of statistical test. So just to back up a little bit, it's been a while since we've really had a real lecture. So this is another type of null hypothesis testing. And so remember, the overall idea here is that we're going to measure some kind of statistic in our real data. And so this could be as simple as a difference in the means. It could be a more complicated kind of statistic, like a Z or a T statistic, something like that. And then what we want to do is compare what we're seeing in our real data to to a distribution that's coming from our null hypothesis. And so the first way we talked about doing this in the class is some kind of brute force simulation or permutation-based method to generate these null distributions. And more recently, we've been talking about trying to mathematically define what these distributions should look like based on some kind of assumptions about our data and assumptions about the null hypothesis. So we talked about using binomial distributions, for example, and last lecture we talked about using T distributions. And so for most kinds of scale data, the assumptions of the t-test are usually reasonably accurate. And so we don't actually have to go through the whole process of doing permutations. We can instead just assume that our null distribution is going to look like this t distribution. And so then no matter how we get our null distribution, we can then compare our real value to this null distribution and ask how unlikely it would be to get this real value in this null hypothesis. And if it turns out that it's very unlikely, that the p-value is very small, then we would reject that null hypothesis and say that we think something is going on in this data that's not accounted for by this null distribution. Okay, so the test we're going to talk about a couple tests today that they still fit in this same framework, but they make a different kind of assumption about the data. And so specifically, one assumption that we made for both the z-test and t-test stuff we've been doing is that we have scale data, and that it makes sense to compute a mean. And so we talked about near the very beginning of the course that there are other kinds of data. So for example, we might have data that we can't compute a mean on. And so the machinery, the kind of mathematical machinery we've been talking about over the last couple lectures doesn't really work for this case, right? That we can't get a mean, we can't get a normal distribution. And so today we're going to talk about what we could try to do if we have only ordinal data. And so remember, ordinal data is data that we can rank. So we can say for any two data points, we can say which one is bigger than the other, but we can't do arithmetic on it. So we can't add things together. We can't compute means, things like that. So the question is, what if we want to do some kind of hypothesis test on ordinal data? So for example, say we have data from two different groups, and we want to ask whether there's some difference between those two groups. So one approach we could do is fall back on our sort of permutation bootstrap ideas. And just instead of using means, we could use medians, right? So ordinal data, we can compute medians in ordinal data. And we could do things like look at the difference in medians between two groups and compare that in the real group, the real set of groups versus a permuted set of groups, right? And so we make lots of permutations. We measure the medians in these permutations and see how they compare to our real groups. But we actually don't necessarily have to fall back on permutations. We could also use what are called non-parametric rank tests. And this is what we're talking about today. So this term here, this non-parametric term, means that these methods don't actually make any parametric assumptions about what the shape of the population distribution looks like. Right. So the parameters here we're talking about is that for the t-test, for example, assumes something about what the shape of our measurements and our population distribution looks like. And so instead of making assumptions about the population, we're actually going to only make assumptions about the ranks. And as we'll see, that making assumptions about the ranks is really easy to do. And so we're still going to make some, unlike the permutation test, we are going to make some assumptions here. We are going to try to work out like a closed form answer to what the p-values are. But we can do this without making any assumptions about the data points we're collecting. This again depends on the particular domain that you're working in, but even if you do have scale data, you might want to still just treat it as ordinal data. So for example, you might have data that breaks the assumptions of a t-test. So for example, if you have a really non-normally distributed population and a small sample, then you might be violating some of the sampling assumptions of the t-test, right? Remember that we need the sampling distribution of the means to be normally distributed, and the central limit theorem won't kick in if the samples are too small. So whether we either don't have scale data or we don't want to treat it like scale data, we can just use it as ordinal data. And so what we're going to do is we're going to take our ordinal data and think about just the ranks of these data. So remember, ordinal data, we can always rank it. We can always say which one is the smallest and which one is the biggest. And the nice thing about ranks is that ranks are, by definition, always going to be uniformly distributed, right? What that means is that if we have n people that run in a race, there's always going to be exactly one person that finishes first. There's going to be exactly one person that finishes second, and so on, right? And so if you think about the distribution of these ranks, right? How many first place finishers are there? How many second place? How many nth place finishers? There's always exactly one. And so we just have this totally flat, uniform distribution of ranks, right? No matter what the actual finishing times look like, the ranks themselves are always going to be uniformly distributed. And so what this means is that we can ignore whatever weird distribution the actual data has, and instead just think about these ranks, which we know are uniformly distributed. And so we can make the assumption that the ranks are uniformly distributed, right? It's not even really an assumption. It's basically guaranteed to be true. Okay, so we haven't talked too much about ranks before. Again, as long as your data is at least ordinal, we can compute ranks. You might be wondering about what if our data is not ordinal? What if it's only nominal? And so we'll talk about that on Tuesday. But here we're assuming that our data is at least ordinal, and so we can compute these ranks. Usually the convention is that we assign lower ranks to smaller scores, although it doesn't really make a difference for the tests we're doing. So yeah, there's a question in the chat about ties, which is a really important point. So What we want to make sure is true is that when we sum up all these ranks, right? So if there's no ties, there should be exactly one rank 1, there should be exactly one rank 2, and so on. And so when we sum up all these ranks, we're just summing up the numbers from 1 to n, which if you remember back to your like arithmetic sum formulas, you probably saw at some point, this is n times n plus 1 over 2 is the formula for the sum of numbers from 1 to n. And so what this means is that the average rank, if we just divide that by n, the average rank is going to be n plus 1 over 2, right? So if you think about if we have numbers from 1 to 10, for example, right, the average of the numbers from 1 to 10, we would just take 10 plus 1 divided by 2. And so what we want to make sure is that we want to make sure that that average rank number is always true, even if there's ties, right? So we have to be a little bit careful with the ties to make sure that we don't mess up this average rank, because the tests we're going to set up assume that the average rank is always n plus 1 over 2. And so, right, the way that we do this is that, first of all, we sort the data. If there's ties, it doesn't matter how those ties are arranged, right? But we're going to sort the data as best we can. We're going to assign ranks to the data. And then what we want to do is average the ranks for any ties, right? So, for example, if our data looks like this, if we have 3 zeros, 2 ones, 4 twos, and a 3, right? We'd sort them, we'd rank them in order, and then we'd average the ranks between all of the things that are the same, right? So for the zeros, for example, they ended up in ranks 1, 2, and 3. And so what we do is we, after this averaging, we just assign all of them rank 2, right? You see the ones got assigned rank 4.5, the twos all got assigned rank 7.5, and the 3 got assigned rank 10. Right. You could also imagine, let's say we have data that's like kind of like Likert data, right? That we have people giving approval judgments. And so we have 2 disapproves, 3 neutrals, and an approve. Again, we can sort these, right? That neutral is in the middle of disapprove and approve. We assign them numbers 1 to 6, and then we average within each of the ties, right? So what this means is that we may not actually have exactly one value for every rank, right? So you could see in this last example, there isn't any data point with rank 1, there isn't any with rank 2 or 3 or 5, right? But we still have this uniform distribution in the sense that the average rank is always going to be, right? In this case, the average rank would be 6 plus 1 divided by 2, or 3.5, right? And that's true. The average rank is 3.5 in this original order. And then after we average within these ties, the average rank is still 3.5. Okay, so we're gonna have a pause here for a quiz. So please type in the chat what you think the answer to this is. So the question is, if we have 10 ordinal values, what will the mean rank of these 10 values be? Also, if you have any other questions about the previous section, now would be a good time to ask, and I can go back and answer any questions. All right, great. I'm seeing a lot of D's, which is good, right? So when we rank 10 ordinal values, if there aren't any ties, then these will just be the numbers 1 through 10, and the average of those is 5.5, which is D. And even if there are ties, we make sure to to average within those ties so that we still end up with the same. Right. What we don't want to do, for example, is if there's lots of values that are all tied for the minimum value, we don't want to assign all of them a rank of 1, because then that's going to make our mean rank be too small. Okay, great. All right, so now let's talk about the actual test. So the first test we're going to talk about, I'm going to refer to as the rank sum test. Unfortunately, for both of the tests we're talking about today, the terminology is really inconsistent across different books and across different software packages. So, for example, in the lab you're going to do today, R actually calls these things slightly different names, which is kind of annoying. But I'll try to be consistent here about saying that this first test we're going to talk about, this rank sum test, is about independent samples of data, right? So this is kind of a similar situation as like the independent two sample t-test we talked about last time, right? Where we have two groups we want to compare. We want to compare the medians of these two groups. And these are two just unrelated, unpaired groups that may even have different sizes, for example. And so, so first of all, we need the assumptions we're going to make here is that the data have to be random samples that are at least ordinal, right? So for pretty much all of the tests we're going to talk about in this class, we're making the assumption that the data has to be random samples, right? Meaning that we're taking unbiased independent samples from the population, and we're assuming that they're at least ordinal, right? Meaning that we can rank them. We also need, for the specific way we're going to work out the p-values, we need the central limit theorem to kick in on these ranks, on these uniform ranks. And so this basically almost always works. If you have a really tiny data set, then you have to basically do some kind of permutation test to figure out the p-values. And R will usually do this for you. So R will, I think maybe R's default threshold is like 50 or something. But if you have a small data set, R will use permutations. And if it doesn't, it'll use a normal distribution, which is what we're going to use. Okay, so the null hypothesis we're testing here is about the population medians of these two samples, right? So remember, if we have ordinal data, we can't compute a mean, but we can compute a median. And so the null hypothesis is that the median of this first group and the second group is the same. The alternative hypothesis is that they're different in some way, right? And again, if we're doing a two-tailed test here, that just means that one is bigger than the other by any amount. And so what we're trying to test is, do we think our data, the data we're seeing, is likely under this null hypothesis that the population medians are the same? So let's first just talk about the intuition for how this is going to work. So what we're going to do is take all of the data from both groups, and we're going to compute ranks with all of this data together. And the idea is that if these two groups have the same median, then the rank should be pretty mixed up between the groups. So for example, here we have some samples from a blue population, some samples from a yellow population. We put them all together and compute ranks across all of them. And so what we can see is that the two smallest values came from the blue population. Then the third and fourth smallest values came from the yellow, and so on and so on. And so you can see they're pretty mixed together, right? That as you're going through these ranks, it sort of alternates between yellow and blue. Right, so this is an example when the two populations have the same median, right? Then we'd expect that the small ranks will sometimes be yellow and blue, and the big ranks will sometimes be yellow and blue. You could also get something like this. So if we had two samples, we have two populations that are coming from two samples from populations with the same median but different variance, you could get something like this, where the blue values tend to be like either really small or really big, but still in this case, the ranks are still centered around about the same value, right? It's still the case that the average rank of the blues and the average rank of the yellows is about the same. But if there are differences in the population, we'd expect something like this. So in this example, the 7 smallest values are all from blue, and the 4 biggest values are all from yellow, right? And if we look at, on average, the blue values here have lower ranks than the yellow ones do. So this is basically all we're going to test here. Is we're going to test, we're going to sum up the ranks of one of these groups. So for example, we could sum up the ranks of the yellow group here, and ask whether those ranks on average are in the middle, right? In this case, the middle would be 10.5. So we're going to ask whether this group has an average rank that's right in the middle of the two groups, or is this average rank sort of too big or too small? That would be evidence against our null hypothesis. Okay, so yeah, so the first step is we put both of our samples together and compute ranks across both of them. And then we're going to sum up the ranks in one of the groups. It doesn't matter which one you do, just to keep it consistent. I'm just going to assume we're doing the smaller group, but you could do it. You could work this out either way. So this is our observed statistic in our data. So remember, our kind of formula for null hypothesis testing is that the first thing we're going to want to do is get some kind of observed statistic in our real data. And so our observed statistic is the sum of the ranks in this smaller group. Now what we have to do is think about what the null hypothesis is here. And so the null hypothesis is that these two groups have the same median. And so all of the ranks in each group should be centered around the average rank. And so the null expected total here is the number of values in this small group times the average rank, right? The null hypothesis is that all the ranks in this one group are all kind of centered around this average rank R bar. And so the expected total of those ranks is just the number of items times this expected rank R bar, right? So now we have our what we actually measured in our data, which is what's the actual sum of ranks in this group. And then we have our null hypothesis, which is that the average rank in this group should just be R bar, right? That's this null hypothesis, is that this both of these groups are centered around the mean rank. So the last thing we need to actually do a test here, right, is we need to not only know where the center of this null distribution is, but we need to know something about the dispersion of the null hypothesis, right? What we need to know is if let's say our observed total is 5 more than the expected total. Is that a lot or a little? To do that, we need to know something about the standard error, right? The standard deviation of this sampling distribution. Okay, so yeah, I'm not going to work out exactly how you get to this, but this is the formula for that standard error, right? So again, computing this doesn't use our real data at all. All we need to know how many data points there are total, and we need to know how many data points there are in this smaller group. And so we just plug those numbers into this formula. That'll tell us what the standard error of this null distribution is. It might seem a little weird that there's a random 12 in the denominator there. Right, and that's not like for this, that's not for any particular example, that's part of the formula. And so one sort of hint about why that 12 shows up is if you think back to the way that the ranks are distributed, right? So ranks are, by definition, always going to be uniformly distributed, right? And if you flip back a few weeks of slides, the variance for a uniform distribution has this factor of 1 over 12 in it. All right, so that's where that comes from. Is we're assuming our null hypothesis here is that the ranks are the ranks are uniform, and our null hypothesis is that the smaller group is just coming from sort of uniformly distributed ranks, right? That the smaller group has some little ranks and some big ranks, and they average out to the middle. Okay, so now we have all of the things we need to actually compute this test. Right, so just to recap the stuff we already did, right? We compute the sum of the ranks in the smaller group. We compute this expected sum and the standard error of this expected sum. And now we can compute just a z-score, right? We can say how far away is what we observed in the data from this null expectation, and then divide by the standard error of our null distribution, right? So again, this is putting this into like z units, which is how many standard errors away from the center of the null distribution are we? And so at least if our data set is relatively big, this z-score is going to be a true z-score, meaning that it's actually normally distributed. And so we can just integrate under a normal curve or use a table or whatever to get a p-value. If our data is really small, then this is not really a real z-score. It hasn't quite converged to a real normal distribution yet. And so instead we'd have to we'd have to do some kind of we'd have to either do a permutation ourselves, or there's like tables you can look up for small values and things. We would, in real life, we would just use R here, and R internally does some kind of permutation test to test this. Okay, right. So the setup here is very similar to a t-test, right? We have the same, we're going to end up with something that's kind of the same form of something we actually measure, a statistic we actually measure in our data, a statistic that is coming from our null hypothesis, right? This TE is not, doesn't have anything to do with our data. To compute TE, you remember all we needed was to know how many items are in this group and what's the mean rank. And then this is also coming from our null hypothesis here, right? Which is the dispersion of our null hypothesis. And so we plug these three things in, right? And this tells us how surprising our data is in units of standard errors. How many standard errors away from the population null mean are we? And then we can look up and see what p-value that corresponds to. All right, time for another quick break. So, all right, the question here is, what value in the rank sum test corresponds to the null hypothesis? So please answer in chat. Also, if you have any other questions about the previous few slides, feel free to answer, and I can always go back to previous slides. All right, I'm seeing some B's and some D's. So the answer I was going for was B, although D is also pretty close, right? So the statistic we're measuring in our data here is the sum of all the ranks in the smaller group, right? That's this T sub S. Let's see. Oh, I made a typo on the slide here. That should say observed total of ranks in the smaller group. And so right, and the way that we get this T sub E, this expected total, is we take the mean rank and we multiply it by the number of values that are in that smaller group, right? So it is true that our null hypothesis is basically that all of the values that the ranks on average in this small group are going to be R bar, the mean rank. But the actual null statistic we're measuring is that T sub E, which is just the mean rank times the number of values that are in there. Right, so B is the right answer. D is also basically right, right? It's just the actual statistic we're measuring here is this T sub S, which is the sum of all the ranks in the smaller group, not the average of their ranks. So for the formula to work out correctly, you want to make sure you're using TE and TS, and then we're dividing their difference by that standard error of TE. Okay, so let's do an example of this. So here's some data that I think we briefly saw during the t-test lecture. We have people that are drinking either coffee or tea, and we want to compare whether these coffee drinkers or these tea drinkers have faster reaction times on some test, or maybe it's how fast they finished a puzzle, something like that. So these are not paired measurements. And so, right, we just have a bunch of people in the tea group, and then we have a separate bunch of people in the coffee group. And so the first step to run this rank sum test is we want to combine across both groups and get ranks across both groups, right? So we're not ranking, there's 10 people in each group here. We're not ranking 1 to 10 within each group. What we're doing is we're putting together all of our values here across both groups, and we're getting ranks across both groups. Right, so the smallest value in our data set is like this fourth person in the coffee group. That was the fastest finisher. The slowest person is this person in our tea group here, right? So we have, so we get ranks from 1 to 20 of all 20 of our participants. And so what we do in the rank sum test is after we have these ranks, we then throw our original data away. The original data, the actual values that we got in our actual data do not enter into this test at all, right? We just use them to figure out the ranks. And then at this point, what we actually were measuring, like the fact that we were measuring in units of seconds, for example, has nothing to do with this anymore, right? We just have these ranks. And so what we want to test is we want to know, does it seem like these ranks are coming from two distributions that have the same median or not, right? What we want to know is, are the tea ranks and the coffee ranks both centered around 10.5 or not? So what we're going to do is, so here the groups are the same size, so we just pick one to call the small group. It doesn't make a difference. And so we are going to sum up the ranks in one of the groups. So let's sum up the ranks in the T group. So all we do is we just add up these numbers from 20 to 12. We add up this whole column and we get 127. And the total number of subjects is 20, and there's 10 in this group. So we can then, so this is our observed statistic, is that the sum of the ranks in the T group is 127. And we can then compute our expected statistic, right, which is just that there's 10 people in this group, and the average rank is n+1/2. So, right, there's 10 people in the T group. The average rank is 21/2, which is 10.5. So our expected sum of ranks is 105, right? What this is saying is that if our T group was exactly centered around the average rank, we should end up with an expected total sum of ranks that's 105. And so what we actually got was 127. And so the question is that like meaningfully different, right? 127, it seems kind of different than 105, but it's kind of hard to say if that's surprising or not, right? We wouldn't expect to get exactly 105, even if this is null data. So we need to compute one more thing, which is the standard error of the mean, right? The standard error of, sorry, not of the mean, the standard error of the expected total. And so again, all we need to know here is the sizes of the groups to plug into this formula. There's 10 people in one group, 10 in the other, 20 plus 1, right? 20 people total plus 1. So we end up with 13.28 as the standard error here. So now we can compute our z-score, which is just asking how many standard errors away from the mean is our observed value. And sorry, I'm sorry, I keep saying mean, right? This is not what I mean is that this is our null hypothesis of expected values, right? We're not actually computing means here. We can't compute means on this data. So so we have our our expected total was 105. Our observed total is 127, which is 1.66 standard errors away from what we expected. And so if we want an alpha of 0.05, that corresponds to a critical z of 1.96 for a two-tailed t-test in the normal distribution. And so you can see we didn't quite make it, right? We're 1.66 standard errors away. We would need to be 1.96 standard errors away for this to be significant, right? So our p-value is like, somewhere, sort of interesting, but doesn't actually cross our significance line, right? So what this is saying is that if we, in this case, the fact that the T group has a sum of ranks that's 127 is not that surprising. It could still be that there's actually no effect here, that the tea drinkers and the coffee drinkers have the same median times. With this data, it's kind of inconclusive. So this rank sum test is comparable to the independent samples t-test, right? They're both doing something similar, which is that we have two separate groups of measurements, and we want to ask whether their central tendencies are different or not. The t-test is doing a test on whether the means are different. This one is doing a test on whether the medians are different. And so, if we have ordinal data, for example, then we would have to use this. Even if we have scale data, again, we might choose to use this if we think that our data doesn't satisfy the assumptions for the t-test. And so the nice thing here is that this test doesn't make any assumptions about what the population distribution of the actual measurements looks like, right? The first thing we do is compute ranks, and then only the ranks go into our test. And the ranks are sort of always well-behaved, right? They're forced to be kind of well-behaved. And so we don't actually care what the original populations look like. Right, and this is not true for t-tests. For t-tests, especially if our sample size is relatively small, for t-tests we do have to have some assumptions about the population. Right, we need the population to either be normally distributed or to be or to have a big enough sample that the central limit theorem kicks in and gives us a normal sampling distribution. So you might ask why we don't just always use this test, right? This test has fewer assumptions than a t-test. If there's data we could run a t-test on, we could always run this on it also, right? And this also handles other kinds of data. It handles ordinal data, and it handles data that don't meet the t-test assumption. So why don't we just always use it? And there's a few reasons. So one reason is that this test never actually sees the real data, and so you can't use it to create a confidence interval, right? We can't, in the example we did, we were collecting data like in units of seconds, but the test itself only ever sees the ranks. So there's no way to pull out like some kind of confidence interval in units of seconds out of this thing. So that's kind of a problem. Getting confidence interval is one of the main things we often want to get out of inference. And so here you could get some kind of confidence interval, but it would be on ranks, and so it doesn't really translate into like the actual units of measurement. So that's one problem. The other problem is a more general problem, which is about power efficiency. And so we're going to talk more about this too in a few weeks. But the definition of power efficiency is if we have two different tests we could use in some sample. Power efficiency, it talks about how sensitive these tests are at detecting real effects. Right. So this basically is all about sort of false negatives and true positives, right? So this is about there really is something in the data and we want to try to find it. And how sensitive are we? How easy is it for us to actually find this true effect in the data? And so what we'd like is that we'd like our test to have really high power. And power efficiency here is basically like a relative measure of power. So for example, let's say we have, for some particular data set, we need like 182 participants to reject the null hypothesis with the t-test, right? So we need 182 participants to actually detect some real effect in our data. We might need more than that if we use the rank sum test. So we might need 200 participants, for example. And so we'd say that the rank sum test has a power efficiency of 91%, meaning that each subject only counts for like 91% of a subject if we had used the t-test, right? We have to collect some extra subjects because we've lost a little bit of power by switching to this test. So the rank sum test actually is not terrible in terms of power efficiency. So for like really large samples, it's actually pretty close to a t-test anyway. For smaller samples, it can sometimes be a little bit lower. So we do lose a little bit of power by switching to this. And this is a kind of general thing that we've talked about a little bit before too, that that if we know some assumptions about our data and we can put those assumptions into our test, that's going to increase our sensitivity to detect true effects, right? The more hands-off we make our methods, the harder it's going to be for them to find true effects, partially because they have to be a little more conservative, right? So if we tell our test fewer things about our data set, then our test needs to be more suspicious that something weird is going on. Our test doesn't know if it sees data that looks like it's kind of weirdly distributed. It doesn't know if that's because the null hypothesis is being violated or maybe that data is just weird. And so this is a kind of general trade-off that we'd like to not impose lots of assumptions on our data. But if we do that, it's going to decrease our power efficiency, right? It's going to make it harder for us to find true effects if we try to not impose assumptions. The trade-off, of course, is that adding assumptions is only a good thing if those assumptions are true, right? If we add assumptions about our data that are not true, then we're getting a p-value that's not really relevant, right? That means that the null hypothesis, the null distribution we're making doesn't really correspond to something that could happen in the real world, right? We're making assumptions that don't correspond to the real world. And so that p-value doesn't really tell us that much. Right. So for example, it's easy to get a really tiny p-value if you impose lots of bad assumptions in your test. Your p-value will be small. It'll say that the null hypothesis with all these assumptions, it can't generate this data, right? But that doesn't really tell you, it doesn't really answer the question you care about, which is whether this data could be captured by a reasonable null hypothesis. And so, again, this is the kind of thing that statisticians in a particular field tend to argue about what are the right assumptions we can make about our data. And ideally, we want to make as many valid assumptions as we can. Okay, so here's a question about what we were just talking about, right? So the question is, what happens to our power or our power efficiency as we add valid assumptions to any test? All right, good. I think everyone's in agreement, right? Which is that adding valid assumptions to our test is a good thing. It's going to increase our power to detect true positives, right? To detect real non-null effects in our data. Right, adding invalid assumptions is going to be a bad thing. It's going to basically give us p-values that are not relevant, right? And so again, there's this kind of trade-off about whether an assumption is valid or not. Depends on your kind of domain knowledge about the field you're working in. It's right. I guess one lesson I'm hoping that you take away from the class is that statistics isn't this sort of like black box thing that you can just dump numbers into and get some value out. A good statistical test can only be done by someone that actually understands where the data is coming from, that has some kind of, right, at least assumptions, hopefully some kind of validated assumptions about what the data is, how the data is being sampled and what the distribution of the data is and these kinds of things, right? And so the more of those kinds of expert assumptions we can bake into our tests, the more sensitive they'll be to detect true effects. Okay. So we're going to talk about one other test today, which is, again, called by a lot of different names. I'll try to refer to this one as the Wilcoxon signed rank test. And so this is a test that instead of applying to two independent populations, is instead comparing paired samples of data, right? So this is similar to the paired t-test. So usually the way we apply this is that we get two measurements for each participant in our study. And these are paired measurements where the same person is being tested two times and we get two numbers for each person. And so our assumptions here is that the data themselves need to be scale data, right? We need to be able to, we're going to want to compute a difference within each person. And we can only do that if this is real scale data we can do arithmetic on. So the non-parametric part is coming in our null hypothesis here, which is that we're going to test whether the median of these differences, of these within person differences, is 0 or not. Right. So our null hypothesis is that on average, and by average here we mean median, on average, people's change between these two measurements we're getting from them is 0. So sometimes there's a positive change, sometimes there's a negative change. There's as many positives as there are negatives. So remember, this is pretty similar to the paired t-test, but the hypothesis here is different, right? For the paired t-test, the null hypothesis is that the mean change within a person is 0. Here, the null hypothesis is that the median change within a person is 0. Right. And sometimes those will be kind of similar, but they could be very different. Right. So if the median difference being 0 means that the number of positive changes is equal to the number of negative changes. The mean being 0 is that the sum of all of these changes is equal to 0. Right. And so, for example, if you have some very large positive changes in your data set, that won't have any impact on this median measure, but it would have a very big impact on the mean measure. And so again, it depends on context, which of those it makes sense to do. and what you think is meaningful, right? So one question is, if someone has a very small, one person has a very small positive increase and another person has a very large positive increase, do you want to count them, just say, okay, they're both positive, or do you want to actually care about the magnitudes or not? Right. And that can tell you whether you should choose a t-test or whether you should choose this signed rank test. Often the t-test is usually kind of the default. Usually we want to say bigger changes are more meaningful than small changes. But it might not be true. There's some kinds of data where you might expect first of all, you might expect lots of kind of weird outliers where some people are like changing an enormous amount, and you don't want that to mess up your test, right? You don't want to have them pull the entire null hypothesis just by themselves. And again, there's also this kind of trade-off of assumptions here, right? The median being 0 is is making a little bit less assumptions about the data, right? It's saying that we only care about the sign of the change. That's where this signed rank test is coming in, right? Is we're only really caring about the sign of the change and not the actual magnitude. Okay, so the way to do this is we first compute the difference scores. And so for any paired test, this is always the first thing we do, is we take our 2 values per person and convert them into 1 value per person, which is the difference. And then we actually throw away the original data, right? We don't actually care what the absolute values of the before and after measurements are. We just care about the difference between the 2 of them. Then the second slightly weird thing that we do is if there's any differences that are exactly 0, we just get rid of them. So this is kind of weird. Some of it has to do with like the math of how this test works. If you're collecting scale measurements, this won't really happen, right? If you're collecting like high precision scale measurements, it's almost impossible you get an exact 0. But if you do, you have to remove those from the data set. Then what we're going to do is create ranks for the absolute values of the differences, right? So we're going to we still have to keep track of the signs here, but when we assign ranks to these differences, we're going to rank them according to their absolute value from 0. And then what we're going to do is we're going to group the ranks in the subset drawn from the positive differences and the negative differences and get their sums. We'll see an example in a second of how we're doing this, right? But the idea is that we want to figure out how many of our, right? So we have all our differences and we're ranking them by absolute value. So the smallest ones here, the smallest ranks are going to go to the things that are close to 0. Biggest ranks are going to go to the things that are far from 0. And so we can compute the sum of each of these 2 groups, right? So what are the sum of these ranks in the negative group and in the positive group? And then we can compare to our null hypothesis. And the setup here is very similar to the last test, right? The null hypothesis is that both of these groups should be centered around the mean rank, R bar. The formula for the standard error here is different, right? But it's a similar kind of setup, right? The null here, we don't need to know any actual information about our real data, except how many values there are. Then we can compute a z-score here. So we can take either group. So by convention here, we're taking the sum of the ranks in the positive group, compare that to our null expectation, and divide by standard error to get something in units of z. And again, we can usually these z's will be like real z-scores that are normally distributed, and we could just use a z distribution, meaning a standard normal distribution, or otherwise we have to fall back on permutations. Okay, so let's do an example. So here's an example where I think I mentioned this during the t-test one. We have students that are they're wearing pedometers, and we're looking at their step change, the amount of steps they're taking on a first day. Then we have them abstain from caffeine for a week, and we get another measurement of their steps. And so these are paired measurements, right? Every subject here, we get 2 numbers. And so that allows us to compute these different scores. And again, we can't do this for like independent samples. If we're getting these measurements from different groups of people, we couldn't compute these different scores. But since we have these within subject measurements, we can compute these different scores for each subject. So you can see some of these are positive, some of these are negative. What we want to know is, right, what we want to test here is the median of these differences 0 or not, right? is the median of these differences significantly different from 0 or not? So after we compute these differences, we now compute ranks. And remember, we're computing ranks here on the absolute values of these differences, not on the numbers themselves. So the smallest value here in absolute value is this one, 101. Right? This subject only changed by 101 steps. So that gets rank of 1. The biggest change was this one, right? And so you can see that, right, the smallest change was this person who increased. The next smallest change was this person who decreased. The next smallest change was this person who decreased, and so on, right? So we give them ranks based only on their absolute values. Notice that any zeros here we have to drop from our data set. So this one person had exactly the same number of steps, so they just get dropped from the data set. We basically just remove their data. Again, I set this to 0 just for the point of an example. As you can see here, this is like kind of unlikely to happen, right? If we're measuring number of steps, the chance of them getting exactly the same is pretty small. But yeah, if you do get any zeros, then this test can't deal with the zeros. Okay, so so in any paired test, right? After we use our original data to compute these different scores, we then throw away that original data, right? So the test here doesn't actually know anything about how many steps on average people are making, right? All we care about is these different scores. And in fact, we don't even care about the value of these different scores either. We just care about their ranks, right? So this is the non-parametric part of this, is that what's going to go in this test is only this rank information. So what we're going to do is we're going to look at the ranks. We're going to divide up these ranks to say which one came from positive changes and which ones came from negative changes. And so you can see in this, right, in this data set, there were 7 positive changes, or 1, 2, 3, 4, 5, 6, 7 positive changes, 3 negative changes, and 1 0 change, right? And so we compute the ranks across both positive and negatives using their absolute values. But now to compute our actual statistic here, we're going to divide them up. So the observed statistic for this data set is the sum of these ranks of the positive changes, which is 46, right? That's just 9 plus 6 plus 5, 7, 8, 1, 10. We could also compute this for the other group. And remember that we originally had 11 subjects here, and we dropped 1 to get down to 10. Okay, so right, so we have our what we actually measured in our data, right, is that the sum of the positive ranks is 46. And now we have to figure out what our null hypothesis is. And so remember, the average rank here is 5.5, right? We only have 10 usable subjects. So 10 plus 1 over 2 is 5.5. And so the expected ranks, the expected sum of ranks in this positive group, we'd expect that exactly half the changes should be positive. If the null hypothesis is true, we should be equally likely to have a positive change or a negative change. So we'd expect that we should be about 5 of the subjects should be positive, and the rank of these changes should be about 5.5, right? So the expected sum of ranks in the positive group should be 27.5. This is also the expected number of the expected sum of ranks in the negative group, right? The null hypothesis here is that they're both the same. So we're expecting that the sum in the positive group is 27.5. We're expecting the sum in the negative group is 27.5. What we actually observed is that we got 46 in the positive group. And again, to know if that's interesting or not, we need to know the standard error. So we can compute that using this formula, which is 9.81. And then we can compute a z-score. We can ask how many standard errors away from our expectation are we? And the answer is 1.98. And if you remember, for a two-tailed 0.05 test, we wanted to get to 1.96, so we just barely miss it here. Right, so, and again, the traditional answer here is that stuff's either significant or it's not. It's a binary decision. If you cross 0.5, it's significant. If you don't, it's not. Of course, that's a little bit silly and right in terms of like actually evaluating the evidence here, right? But yeah, at least by that standard threshold, we'd fail to reject. Although, right, this clearly is saying that this result is somewhat unlikely under the null hypothesis, right? It could, 6% of the time, this could have happened by chance, meaning that if the population medians are the same, you still could have gotten you could still be 1.89 standard errors away sometimes, but right, this looks like there maybe is a real effect here. We just don't have super strong evidence in support of it. Okay, so yeah, so just to compare to the paired t-test, again, this is running on similar kinds of data. Right, and in fact here, right, we need the data, the original data needs to be scale data here so we can compute differences. We just need those differences to be kind of ordinal data, right? We're just going to rank those differences later on. So the difference scores is what we're actually doing inference on, and this Wilcoxon signed rank test doesn't require any assumptions about what the distribution of those differences looks like. So it could be that, right, maybe some of our participants are going to have like an enormous positive change. This test doesn't really care about that, right? We're only looking for whether the median change is 0 or not. We also don't suffer that much from power efficiency. So compared to the paired t-test, we usually don't. We usually have like close to the same power. And we also have the advantage here that this is applicable in more situations than the paired t-test. So in general, the Wilcoxon test is kind of usually like almost as good or better than the paired t-test, right? It makes fewer assumptions, but it doesn't suffer that much on power efficiency. Really, the only big downside is confidence intervals, right? So again, this test only ever sees the ranks of the differences. You can't get a confidence interval out. Like in our example, we couldn't get a confidence interval in units of steps out of this about how many steps we think caffeine is changing people's walking. And that is kind of a problem. We usually like to get confidence intervals, right? It helps us understand not just whether we think the difference is significantly different from 0 or not, but it tells us like what we think the difference is, which is usually kind of relevant. So this, again, is the reason that the paired t-test often is people's first choice if you can use it, right? If our difference scores are either we can make the assumption that the difference scores are normally distributed, or we have a big enough data sample that the sampling distribution of the means of those different scores is still normally distributed. Again, it depends on the context. There might be cases where we don't think that the absolute value of, we don't think that the magnitude of the different scores is super meaningful, right? We just want to know, we just think that, right, we just want to know basically how many are sort of positive and how many are negative. Right. The absolute values do come in when we are computing the ranks. So having we do end up sort of comparing small negatives to small positives, but if we have like large outliers, for example, so there's some very large positive changes or very large negative changes, those won't distort our ranks in the same way that they would distort our means. Okay, time for one more quiz. So this one, there's 4 statements here. And so please say which one is false about the Wilcoxon test. The other 3 are true. All right, great. So yeah, the answer I was going for here is D, that the right. So this test doesn't require any assumptions about what the actual population of different scores looks like. So A is that it uses a single value per subject. And so, right, usually the actual data set might have two values here, like a before and after one, right? But all that this test ever sees is the difference score, right? Before we even get into the ranks or anything, we compute these difference scores. And so all this test cares about is the difference score. We just compute that ourselves in our data set, and then we throw away the original data. It's testing whether the population median difference is 0. It does require assumption C, which is that it's assuming that the data points are independent draws from the population, right? Meaning that, and by data points here, I'm talking about people, right? So, or these different scores, for example. So I'm assuming that we're selecting people for our experiment in an unbiased random way, and we're selecting each person independently. If that's not true, that would actually, we would need to change, for example, this, we would need to change this formula here, right? This formula about the dispersion in our null hypothesis requires that that uses the assumption that our data points are all independent from each other. If they're not, then this variance would actually change. It would probably get a lot larger depending on the situation. Okay. All right, sorry, let me just switch back here. Okay. So, all right. Excuse me. So, there's one last thing I wanted to talk about. This is another kind of another way we might use non-parametric ranks. And so, and this has to do with correlations. So if you remember back when we were talking about Pearson's correlation, there were like all these assumptions for correlations and regressions that if we disobey any of those assumptions, then we're violating the kind of inferences we can make from these things. We talked about a whole bunch of different ways that there can be problems, but one specific way that is often a practical problem is that this Pearson correlation can be really sensitive to a single point in your data set. And so, these sort of having like a single outlier, it's a problem anytime we're computing means, but it can be really bad for correlations. Data set, which includes both this sort of like well-behaved cluster down here and this dot out here, the correlation for this whole data set is actually positive 0.75, right? If we fit like a best fit line to this, it would look sort of like this, right? That most of the variance in this data set is, are you over here or up here? And so the correlation is capturing, it's saying, in general, there's a positive correlation. You're either in this bottom left chunk or you're in this top right chunk. But if we remove this data point, then within this little bottom chunk, there's actually a negative slope here, right? Within this little bottom section, we have a correlation of negative 0.75. Right? It's kind of a little related to like the Simpsons paradox stuff we talked about, right? That there's kind of like two groups here. There's like the actual group, which is like this good data. And then there's this like garbage data point that somehow got in our data set. And if we include both of these types of data in our correlation, it actually entirely flips the sign of this correlation. So how can we deal with this? So one way to try to deal with this would be to try to like remove outliers in some principled way. This gets a little bit tricky because we want to make sure we're not just removing points that don't agree with our hypothesis, right? That's not a good way to do stats. Another approach is leave the outliers in the data, but instead of computing Pearson correlations on this original data, we're going to compute correlations on their ranks. And so instead of trying to actually deal with the real scale measurements here, all we're going to do with this kind of correlation is testing whether our data are monotonic, meaning that whether every time X increases, does Y consistently go up or down? And it doesn't have to be by a specific amount, right? So a linear regression, which is what we're basically doing with correlations, right? A linear regression assumes that every time we move over 1 unit in Y, we're going to move over some set number of units in X, right? That's the slope of our line tells us every time we move 1 unit in in X, how many do we move in Y? Here we're going to throw away the actual absolute values of the measurements. We're just going to care whether whether every time we move in a positive direction in X, do we tend to move in a positive direction in Y, right? Or every time we move in a positive direction in X, do we tend to move in a negative direction in Y? Right? Or when we move in a positive direction in X, is it kind of unpredictable what happens with Y? That would be that would give us a correlation near 0. So this type of correlation is called Spearman's rho, where rho you'll see is this like kind of curly P symbol, and so we have data where we have 2 measurements for every data point, right, that are paired up in some way, and all we do, the Spearman's rho is a kind of a fancy name for a really simple process, which is that all we do is we take our X values and convert them into ranks. So we take all the X values, convert them into ranks among the X values. Then we take our Ys and we convert them into ranks among the Ys. We're never mixing X and Ys here, right? And then we just compute Pearson correlation using our rank data. So for example, there's a bunch of ways of doing this. Here's one of the formulas back from our Pearson correlation lecture, right? So instead of using our actual X's and Y's, we're going to use the ranks of the X's and Y's, right? So we kind of take our data set and we replace the real values in our data set with these ranks. And then we do correlations among the ranks instead of the original data, right? So the actual math here, right, all we're doing is Pearson correlation. We're just doing this kind of like pre-processing step where we take our data and convert it into ranks before we do the correlation. So right, what that's going to do basically is it's going to say that we don't care we don't actually care about how big intervals are between our data points. We just want to know which ones are the smaller ones and which ones are the bigger ones. So for example, here's our raw data, which remember had a correlation of 0.75. And now this is what the rank transformed data looks like. So right, what we've done here is converted all our X's to ranks between 1 and n. We've converted all our Y's from ranks to ranks between 1 and n, right? So it's not labeled on the plot here, but like this x-axis here is now, this is 1 and this is n over, or yeah, this one's n over here. And same for the y-axis, right? That we go from 1 to n. And so here you can see that this outlier is still like a little bit weird, but it's much closer to the other data now, right? It's not possible to get a data point that's like super far away from your other data here because we're forced to use ranks, right? So it's not possible to have a rank that's like very far away from your other ranks. And so in this rank transform data, we now have a Spearman correlation of negative 0.54, right? And so what this is telling us is that there is like this one wildly different point, right? But for most of the time, when we increase X, we decrease Y by some amount, right? And so again, which of these is the right thing to do might depend on the situation. Often what we care about more is, we often care more about the thing on the right? We might care more about whether increasing X leads to some kind of consistent change in Y, but not always. I mean, if this data point is a real data point, then this is potentially worth thinking about, right? Maybe there is some kind of Simpson's paradox thing happening here where there is something that's really different and it's kind of hidden here, which is a bad thing. Or it could just be that we think this interval here, this like huge gap in the X and this huge gap in the Y is not actually super meaningful, right? Like just something about the thing that we're measuring means that sometimes the values can get really big. And it is meaningful that this is bigger in X and Y, but it's not actually like as enormously bigger as it appears on this plot. And so, again, it depends on the situation. People, they're within a particular field, people like to have arguments about this. For example, one place this comes up in the kind of neuroimaging research that I do is we might want to compare, say we show a bunch of images both to a monkey and to a computer model, and we get brain responses from the monkey and we get some kind of responses from our computer model. We want to compare between the two of them. We often might use something like Spearman's rho, right? That we want to say, if this computer model responds really strongly to some images, we're going to expect the monkey brain also responds really strongly, but we don't expect it to be a linear relationship, right? Like these two things we're measuring, they're like very different units and they're probably not scaled the same. And like computer numbers have a much bigger range than the monkey brain recordings do, right? And so we might think it makes more sense to just compare the ranks of these things. Again, it depends on how we think it depends on our understanding of what the data is. All right, so we're gonna do one last quiz. So one of these statements is true about this Spearman's correlation. And so try to pick which one is true. All right, so I'm seeing mostly A's, which is correct, right? This uses only rank information about X and only rank information about Y. It doesn't use the original values. Otherwise, this is exactly the same as a Pearson correlation. So it's going to take on values between -1 and 1. It doesn't have to be positive, but it can't be bigger than 1 and it can't be less than -1. It also can't handle data sets where we have missing values, right? It assumes that every data point here has both an X and a Y coordinate. What is going to pop out of this is going to look exactly like a Pearson correlation. We're just applying it to this weird data set we created where we took our original data and turned it into ranks, and we fed that rank information into our Pearson correlation. All right, so I'll sum up, and I'm happy to take any other questions about any of the previous parts if you have them. So these non-parametric tests are going to, instead of using our original data or our original differences within a person, we're going to use just ranks. There's this rank sum test for looking at whether the medians differ between two independent samples, or the signed rank test for looking at changes within a person, so paired samples within a subject, or these paired samples could also be, if our samples don't have to be a person, they could be something like some particular stimulus item, for example, right? But we're going to compute this single value, which is some kind of difference within each of our data points, and then apply this rank test to see whether that median difference is 0 or not. We can also apply correlations on ranks to look at associations, which are going to be less sensitive to outliers because they ignore the actual values and only care about the ranks of those values. So these are good tools either if the data you have is only ordinal. So the rank sum test can work on ordinal data. The Wilcoxon test requires that it requires that the differences are at least rankable, right? Usually we're going to apply it to scale data and we subtract it, right? But this can also work if we're violating one of the assumptions of our t-test. The most common one is this assumption that the population distributions are normally distributed. And so what we lose here is we lose a little bit of power to detect true effects. We also lose confidence intervals, which is also sad. But they're more generally applicable. Again, you could always just fall all the way back to the stuff we did in the first third of the class, the like permutations and bootstrapping and things like that, right? We could do permutation tests on medians. That's also totally fine. But yeah, then it does require like us sort of brute force generating these distributions. These you could just plug into this to a function in R. All right. Any last questions? All right, so after finishing this lecture, you're ready to start on the next homework and the lab. Again, the lab due date is listed for tonight at midnight, but please just finish it whenever you can. Feel free to either join the scheduled lab hours for the TAs or other make scheduling for other times. And yeah, and again, if you're having any trouble getting access to the course materials or things like that, please let us know and we could try to work something out. All right, so the next live stream will be Tuesday. I'll send out the link around the same time. Yep, I'll see you then.